question. Okay, so negative 5 times u.
Recorded.
What's that? I'm sorry, somebody have a question or comment or something? Okay. Negative 5 times 1u is negative 5u. Negative 5 times a negative 4 is a plus 20. Now on the right side of our equation, all we have to do to simplify it is we do have we're minusing off this u minus 3. I like to think of it as being like a negative 1 that needs to be distributed in here. So we're going to have 11. Negative 1 times 1u is minus 1u or minus u. Negative 1 multiplied by a negative 3 is a plus 3. So we distributed on the left and the right, further simplifying the left side by combining like terms. These constants need to be combined. On the right side, these constants need to be combined. 11 plus 3, that's us 14. And now we have both sides completely simplified. The next thing we need to now do is separate. We need to separate our variable terms on one side of our equation and constant terms on the opposite side. I personally prefer to get the variable on the left side of the equation. It doesn't really matter. You could get it on the right side if you want to, but I'm going to get over the left side. So the first thing I'm going to do here, I'm going to move this minus 1u over to the left side of my equation to join the minus 5u. To do that, we have to add 1u to both sides. The inverse of subtraction is addition. So I'm going to demonstrate that I'm adding 1u to both sides of my equation using the horizontal format. Now, negative 5u plus 1u, these combine to give us negative 4u. On the right side, the u's drop out to 0. Negative 1u plus 1u is 0u. We just say the u's cancel out, leaving us with 14. All right. Continuing to separate, I have my u on the left side of the equation, but I must move this constant 22 over to the right side. So to do that, we subtract 22 from both sides. This would be the vertical way of showing you're going to subtract 22 from both sides. Feel free to write it out horizontally also if you want to do it that way. Now the 22s on the left cancel out to 0, leaving you with negative 4u. And on the right side, we have 14 minus 22, which is going to give us negative 8. Finally, to solve for u, we have to get u all by itself on the left side of our equation. And since this is negative 4 times u, the inverse of multiplication is division. So I will divide the left side of my equation by negative 4. But if I divide the left by negative 4, I also must divide the right side by negative 4. The left side reduces down to 1u or just u. And negative 8 divided by negative 4 nets us our solution of positive 2. And we're done. We have solved that first degree or linear equation. It's called a first degree equation because u throughout the equation is raised to the first power. All right. Now, when you solve these first degree equations, you're either going to get one solution, no solution, or infinite number of solutions. I'll try to demonstrate one of each type. Of course, this one provided us with just one solution. Another way to represent the solution to this equation is to represent it as a solution set. Sometimes authors use braces and include the solution or solutions inside the braces. So this would be a more formal way of representing the solution set to this equation up here. I'll take it either way. All right. All right. And if you do have time, which I'm not going to demonstrate, but you could check your answer. You could put the 2 back in here for you and here for you, and then demonstrate that the left side is equal to the right side upon simplifying, and it should be. Any questions how I solve that equation for you? If you've never solved an algebraic equation like this, a first degree equation or a linear equation ever in your entire life, ladies and gentlemen, you're probably you're in the wrong course. I mean, all of us should have solved at least a simple first degree equation somewhere in our hopefully not too distant past. All right. Okay. Any questions how I solve for you there? All right. We all done with this one here then? Okay, try another one here. Now, this next equation, first degree or linear equation, is going to have decimals. And decimals slow us down, so do fractions. And therefore, I would strongly recommend that if your equation is littered with a bunch of decimals, I would recommend that you get rid of the decimals as soon as possible to make your life easier. I have a decimal here and I have a decimal here. Now, the only way we make a decimal become a whole number is if we multiply it by an appropriate power of 10. If you multiply a decimal by 10, you shift the decimal point one place to the right. If you multiply a decimal by 100, the decimal point gets shifted 2 places to the right. If you multiply a decimal by 1,000, the decimal point goes 3 places to the right. So bare minimum, to eliminate all my decimals, what do I have to multiply both sides of my equation by? 10? Is 10 good enough to get rid of all the decimals? The answer is no, because this will still be 0.5. So it looks like we're going to have to multiply both sides at least by 100. Let's do that. Let's show that step by writing this on our paper. This is showing that we're multiplying this term by 100. We're going to multiply this term by 100. And you're going to multiply the right-hand side by 100. So this is showing that we're multiplying both sides by 100. Now 100 times 5/100ths y gives us a nice 5y. 100 times 200ths gives us a nice whole number of 2. Now some of you are probably thinking, why don't I also distribute the 100 inside the parentheses here? Well, the answer is because the only reason why I'm multiplying this entire term by 100 is to get rid of the decimal. So you can only multiply 100 by one of these factors. I chose this one to get rid of the decimal. It's the same thing as if you had like 2 times 3 times 6. You wouldn't multiply 2 times 3 and also 2 times 6. You wouldn't do that. 2 only gets multiplied by one of these factors. Same thing here. 100 only got multiplied by this. That's it. On the right side, we have 270 times 100 is 27,000. Now we continue to solve for y by simplifying the left side further by using our distributive property, distributing the 2 inside the parentheses. So we have 2 times 6,000 is 12,000. 2 multiplied by a negative y is a minus a 2y. And that's equal to 27,000. Combining our linear first degree terms on the left side of the equation, 5y minus 2y, that's us 3y. And now, since both sides are simplified, it's time to separate variable terms on the left from constant terms on the right. So I'm going to move this 12,000 over to the right by subtracting it from both sides. $12,000s drop out on the left to 0, leaving you with 3y. Technically 3y plus 0, which is just 3y. And then 27,000 minus 12,000 on the right side is going to be 15,000. Finally, to solve for y, to get y all by itself, I need to divide both sides of my equation by 3, since the inverse of multiplication is division. And therefore, this implies then that when I do that, that y is going to be equal to 5,000. And we are done. That would be your solution to that equation. Any questions? How I solve that first degree equation for y?
Would we have to like divide by 100 or something since we multiplied it?
No,
In the beginning?
because I multiplied both sides of my equation by 100, this equation, this resultant equation here is still equivalent to the original equation.
Oh, okay.
So in the end, we don't have to compensate. All right.
All right, cool.
So again, to recap quickly, how did I do this? I wanted to get rid of my decimals real quickly, and to do so, therefore, I multiplied both sides by 100. That cleared all my decimals out of the equation, leaving us with a much nicer equation to then solve for the variable y. All right, so that's a classic decimal equation there. You don't have to get rid of the decimals. You can work with them if you want, but it sure is nice to knock ugly decimals out of the picture. And again, that can always be accomplished by multiplying both sides of an equation by an appropriate power of 10. If your smallest decimal in an equation was like this right here, then you'd have to multiply both sides of the equation by 1,000. If your smallest decimal, let's say, in your equation was like this, then it's good enough to multiply both sides by just 10. Okay, so it depends how small your decimals are as to how large of a power of 10 you must multiply both sides by. All right, do we all have this here? Good on this? Okay. Let's now look at solving an equation that has fractions in it. And because of that, we would classify this equation as being what's known as a rational equation. A rational equation is an equation that contains rational expressions. Rational expressions are fractional expressions. So we want to solve this equation for the variable x. Notice we have fractions here, 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 and this 2 could be placed over 1, no harm done. Fractions are just as messy as decimals. It would be nice to get rid of all these fractions first to make our life easier. The magic bullet for eliminating fractions is called the least common denominator. So what I'm going to do is I'm going to eliminate all these fractions by multiplying both sides of my equation by the least common denominator or least common multiple of 1, 3, and 7. And what's the smallest number that 1, 3, and 7 all divide into? We need a least common multiple of 3 and 7. Multiples of 3 would be 3, 6, 9, 12, 15, 18, etc. Multiples of 7 would be 7, 14, 21, 28, 35, etc. The smallest common multiple of 3 and 7 would be 21. So that's what I'm going to do. I'm going to multiply both sides of my equation by 21. 21 can really be expressed as 21 over 1, same thing. Got to multiply this term by 21. So when you multiply both sides by 21, you're going to multiply each term on both sides by 21. This should be plus 1. And then 21 times 2 here. Now, the point of multiplying both sides of your equation by 21 is to eliminate all your fractions. So that's the intention. So let's see how that works. Now, if you're not into cross canceling, what you could do is when you multiply these together, you could express it as 21 times quantity x minus 6 over 3. 1 times 3 is 3. Express this like this. 21 times this fraction would be 21 times x plus 1 all over 3. And 21 times 2 is 42. So look, you can get rid of these fractions now one of two ways. If you're into cross canceling, it, in all honesty, is the more efficient way to go. 3 divides into itself once, divides into 21 7 times. Or you could say 21 divided by 3 reduces down to 7. In either case, this first term is going to become 7 times x minus 6. Fraction is gone. Whether you reduce 21 over 7 or cross cancel with 7 and 21, you're going to be left with 3 times x for the second term. Fraction gone. Whether you reduce 21 over 3 down to 7 times x plus 1 or cross reduce, cross cancel, 3 goes into itself once, divides into 21 7 times, you'll be left with 7 times quantity x plus 1. Everybody see how we cleared all the fractions out of our equation? So all the fractions are gone now, and we have a nicer equation to work with. Further simplifying the left side, we're going to have to remove these parentheses by distribution. 7 times x is 7x. 7 multiplied by a negative 6 is a minus of 42, plus a 3x. 7 times x here is 7x. 7 times 1 is plus 7, plus the 42. Further simplifying the left side by combining like terms, 7x plus 3x combines to give us 10x. 7 plus 42 combined to give us 49. And now we just have to solve for x here. Now it's time to separate our variable terms on one side and constants on the opposite side, since there's no more simplifying we can do on either side. To do that, I'm going to subtract 7x from both sides to bring the 7x over to the left to join the 10x. 10x minus 7x, that's us 3x. And on the right side, these 7x's drop out to 0, leaving you with 49. Continuing to separate, let's move this constant term, negative 42, over the right side of our equation by adding it to both sides. The 42s add up to 0 on the left side or cancel out, leaving you with 3x. And on the right side, we have 91, I believe. Finally, we're going to get x by itself now by dividing both sides by 3. And therefore, this implies that x is equal to 91/3. Just leave it like this. You don't have to turn it into a mixed number. Notice that is reduced. You cannot reduce that anymore. So just leave it like that, and that'd be your solution. And again, if you feel like putting your solution or solutions inside braces, be my guest. No problem. Okay. Any questions how we solve that fractional equation for the variable? And we did so by getting rid of our fractions first by multiplying both sides by the least common denominator, which in this case was 21. Any questions how we handle that one? I would strongly recommend that you try not to take too many too many shortcuts or cut too many corners when you're trying to solve equations. Shortcuts and too many frequent corner cutting often leads to errors. Okay, so just try to remain patient and lay your steps out on your paper. That way you stay out of trouble. All righty. Any questions about that one there? All right, now there's two examples of a situation that could arise from time to time, although it's rather infrequent in here, but you never know when you're going to experience this. And so I'm going to demonstrate those two special cases next. All right. All right. Suppose we want to solve this equation for the variable t. All right, so we're going to follow the guidelines that we used on all the other ones. The left side cannot be simplified, nothing that we can do over here. But on the right side, we're going to have to use our distributive property to remove these parentheses here. So we're going to distribute the 2 inside the parens. So 4 times t is 4t, and 4 times a -1 is a -4. Further simplifying the right side by combining like terms, we have 4t minus 2t, nets us 2t. And a -4 minus 1 gives us a -5. Everybody understand how we got down to here? Now that both sides are simplified, it's time to separate variables on the left versus constants on the right. To do that, I'm going to have to move this positive 2t to the left side of my equation. The inverse of addition or positive is minus, so we minus 2t from both sides. The 2t, and something weird happens here. I did everything legal, and what's happening here is I'm losing my variable t on both sides of my equation, and I'm just left with this numeric expression here. Well, if this ever happens when you're solving an equation where you lose your variable you're trying to solve for, and you're left with a numeric statement, you want to ask yourself, is the numeric statement true or false? This is a false statement. Because it's a false statement, we did everything legal, utilizing equality properties in our attempt to solve for t here. Ladies and gentlemen, we would say that this equation has no solution. So there would be no solution here because we end up with a false numeric statement here. So this is basically saying that the left side of the equation will never be equal to the right side of the equation for any value of t. Such an equation as this that has no solution has a name. It's called a contradiction in mathematics. So this is an example of a contradiction. That's a contradiction. So once in a while that happens. You might, go about business solving an equation and discover that you lose your variable that you're trying to solve for, and you end up with a false statement. If that ever happens, just basically end the process and conclude that there's no solution to the equation. All right, we'll try to solve this equation for the variable c. Nothing going on the left side as far as simplifying is concerned. But on the right side, we're going to have to distribute the 3 inside the parentheses. So 3 times 1c is 3c. 3 multiplied by a -1 is a -3. So we have negative 5 plus 3c. On the right side, we combine our like constant terms. Negative 3 subtract 2 is going to be negative 5. Questions how we got to here? All right, now I'm going to subtract 3c from both sides, as I'm going to separate my variables on the left from the variables on the right. But just like with the last equation, something strange happens here. We lose our variable c on both sides of our equation. But unlike the last equation, we're left with not a false numeric statement, but we're left with a true numeric statement. And because of that, ladies and gentlemen, we did everything legal, lost our variable, and are left with a true numeric statement. We would say that the left side of our equation will always be equal to the right side, no matter what we put in for c. So we would say the solution set is all real numbers. So this equation has an infinite number of solutions. Any real number that you replace c with, the left side of the equation will always be equal to the right side. That's a way of saying all real numbers. Or you could say the solution set is a set of all numbers c, such that c belongs to the set of real numbers. This funky looking R script represents the set of real numbers in mathematics. So this is a more formal way of representing the solution set to such an equation as this. Again, the solution set is a set of all numbers c such that c is any real number. C belongs to the set of real numbers. This symbol means belongs to. You see that symbol in set theory, okay? Belongs to the set of real numbers. Such an equation where all real numbers are solutions is called an identity in mathematics. So this is an example of an identity. It's an identity because the left side is always identical to the right side. You can clearly see it down here where the left side literally is the same thing as the right side. That's why all real numbers satisfy this equation here. So once in a while you run into a contradiction versus an identity. It does happen. Not very often, like I said, but once in a while you may do that. Okay, any questions up to this point here? All right, now we're going to get a little bit more serious about solving rational equations. We did solve one previously, but that rational equation never had a variable appearing in any denominator. This one's different. This one has variables showing up in our denominator. This is called a rational equation because it's an equation that consists of rational or fractional expressions. And we want to try to solve this rational equation for the variable c. When we solve rational equations, there's a couple of things we need to do first. First of all, we need to make sure our denominators are completely factored. Well, we're lucky here and here. These are already completely factored, but this is not factored. This needs to be factored. Did anybody discover the factoring toolbox that I placed on Canvas? I put a link on Canvas that takes you to the factoring toolbox, which is a flow chart. Anybody have a chance to look at that or see that? Or yeah. Oh, somebody did. Okay, just making sure it's there. Well, how would we factor this? This is a binomial. Might it be the sum of squares or the difference of squares? It appears to be the difference between perfect squares, 9 being a perfect square of 3, c squared is perfect square of c. So therefore, c squared minus 9 factors into the product of these conjugate binomials, c plus 3 times 3 minus 3, c minus 3. Now that we have our denominators completely factored, we need to now maybe consider what kind of restrictions have to be placed on the variable c. We have to make sure that none of these denominators ever become 0. And to ensure that, we have to make sure that c is never equal to what? Well, this denominator has c plus 3 in it. And if we solve this equation for c, we get c is equal to negative 3. But ladies and gentlemen, we don't want c plus 3 to ever be equal to 0, because if it is, then dividing by 0 causes this entire equation to be undefined. So we got to make sure that C is never equal to -3. That's one restriction we must impose on this rational equation. Another restriction is we need to be careful to have this denominator never go to 0. Well, when would that happen? To find out, take C minus 3, set it equal to 0, solve for C, and you'll see that this denominator becomes 0, and my whole equation becomes undefined when C is equal to +3. So we must also insist that C never be equal to +3. These are the restrictions that are placed on this rational equation so that it will remain defined. All right. Another thing we need to do now is get ourselves a least common denominator. And what would that be? Anybody want to weigh in as to what we're going to need for our least common denominator? We need to form an expression that's going to be divisible by all of our denominators. Therefore, what will we need? What factors are we going to need in our LCD? Anybody?
C minus 3, C plus 3.
That's exactly right. We're going to need a C minus 3, and we're going to need the binomial C plus 3. We're going to need both these factors because this expression now is divisible by C plus 3, C minus 3, and it's divisible by this denominator too. So that is our least common denominator. What I'm going to do now is I'm going to get rid of all my fractions by multiplying both sides of this rational equation by my least common denominator. This step, as laborious and tedious as it is, I would strongly recommend that you put it on your paper. Try not to become impatient when solving some of these equations. Impatience usually leads to bad things, not just in math, but in general in life too. So here we go. Just have a little bit of patience, write this step out. Got to multiply the right side by that also, by the least common denominator. I'm putting the least common denominator over 1. You can always put any quantity over 1. It's still the same quantity. All right. A lengthy but necessary step. Now, ladies and gentlemen, how are our fractions going to disappear? Well, they're going to disappear through reducing or cross-canceling. I'm not going to put another step in here and go and show how we would reduce. If you're into reducing, you go ahead and do that. But I'm just going to cross-cancel. This C plus 3 divides into itself once, takes out this C plus 3 by dividing into it once. And we're left then with 2 times quantity C minus 3. Fraction gone. This fraction is gone. Minus, here we can cross-cancel the C minus 3. C minus 3 divides into itself once, divides into C minus 3 up here once. We're left with C plus 3 times 1. Don't forget your minus sign here. So I'm left with quantity minus C plus 3 times 1, or minus C plus 3. Fraction is gone. Equals, over here, both the C plus 3 and the C minus 3 cross cancel out, leaving you with 1 times 10, which is just 10. Fraction gone. Everybody understand how I got rid of all the fractions? Now we just have a simple equation in C to solve. So I'm going to have to distribute here. So we have 2C minus 6. Distributing a -1 into both these terms. -1 times C is minus C. -1 times -3 is plus a 3. Equal to 10. Further simplifying the left side by combining like terms. 2C minus 1C is just C. And -6 plus 3 gives us minus 3. And that's equal to 10. Finally, ladies and gentlemen, I add 3 to both sides of my equation. 3's drop on the left, and I get C is equal to 13. And that is my tentative solution. Tentative because we got to make sure that our solution 13 does not violate one of our restrictions. Does 13 violate our restrictions up here for C? And the answer is no. So we're good. So we retain this as a solution, and the only solution to our rational equation. 13 is your solution, and we're done. Now, had I gone through this whole solution process and I got a solution of 3, I would have to toss it out because 3 violates our restriction here. So it is possible to have a rational equation have no solution in the end, because you may have to toss out one and or more of your tentative solutions because of the violation of any restriction. So again, it is possible for these rational equations not to have any solution. This one had precisely one solution of 13. Questions how I solve this for C? Any questions? Is it making any sense here? What happened? So first, I factored all the denominators. Secondly, I placed restrictions on the variable C. Thirdly, I found the least common denominator. Fourthly, I multiplied both sides by the LCD to knock out the fractions. And then last, I solved a simple equation for the variable C.
I have a question.
Go ahead.
So why did you distribute the -1 into C minus 3? I thought it was supposed to be distributed into C plus 3.
Supposed to be what, you thought?
Distributed into C plus 3 because you canceled out the C minus 3.
Let me see something here. Back up here, I canceled out the C minus 3s, and this should have been C plus 3 left behind. You are right. Did anybody else catch that little glitch? I do apologize. There's my Monday glitch for the day, ladies and gentlemen. You are correct. Back up here, I canceled out the C minus 3s. I should have been left with C plus 3. This should have been C plus 3. I do apologize. That makes this, when you distribute the -1 and the 3, this should be negative C minus 3. This should be minus 3. And therefore, we would have 2C minus C is still C, but -6 minus 3 should be what? A -9, correct? All right, so therefore, 2C minus C is C. -6 minus 3 is -9, and that's equal to 10. Now I will add 9 to both sides, and I get my solution as being 19. Thank you for pointing that out. Notice 19 does not violate any of our restrictions up here, so we're good. This would be your answer, 19. All right. So that also illustrates not only do we have to be patient, but we also have to be vigilant. We have to basically persevere to the end, in the sense that math requires that we have our attention on the problem at all times. Any other question about how we solve for C? The solution should be 19. Do make that change, please. All right. And notice we keep that solution because it does not violate any of our restrictions here. All right, any other questions on this one here? Okay. All right, let's see, what time is it? 1:07. Okay, another thing that we are going to look at briefly in here is how to solve what are called formulas. There's thousands and thousands of formulas being used all around the planet as I speak, ladies and gentlemen, to take care of various types of businesses. All right. What is a formula? A formula basically is an equation with 2 or more variables present. There's no way you can get through any sort of science class and not run into a formula. It's impossible. Science courses are littered with formulas. You take a course in chemistry, you're going to run into formulas. You take a course in physics, there's going to be tons of formulas in physics. You take a course in nursing dosage calculations, you're going to run into formulas. All right. Those apps that we tap on our phone and do wonderful things for us, ladies and gentlemen, you wouldn't believe all the mathematical formulas that are behind the scenes that have been programmed in to make that app perform the way it performs. There's a lot of math behind the scenes of using those apps on our phone. Tremendous number of formulas are used, okay? And variables enable amazing things to occur in our technological lives every day. And so basically, I know this sounds strange, but pretty much everything in our everyday lives boils down to some sort of a mathematical formula or variable. In a large sense, it really does. Okay, there's a lot of math behind the scenes out there being played out on a daily basis in our lives. So, ladies and gentlemen, what we're going to do here now, the nice thing about this is you don't really need to know what these formulas pertain to, but what we do need to know how to do is solve for a particular variable. And this is a survival skill. If you go into the computational sciences or any sort of engineering, you're going to be manipulating formulas all the time. Even computer programmers that are going into software engineering, they have to know how to solve a formula for a particular variable before they present it to a computer system using pertinent language, okay? So computer programmers, it would be wise if you're going into computer programming to take as much math as you can possibly take. All right, so ladies and gentlemen, here is a formula, and what we're going to do is try to solve this formula for the variable A. Presently, this formula is solved for what variable? Anybody want to weigh in? What is this formula solved for presently as presented to us? It is solved for what variable presently?
S.
S, because S is all by itself on one side of your equation. We're going to turn the tables on this and solve it for A, but we have to do quite a bit of algebra to get there. All right. Now, does anybody have an idea as how we could get started in solving for A? How we'll get started in stripping this right side down to eventually lonesome A? How can we do that? Any ideas? Anybody have any ideas how we can jumpstart this here? Solving for A.
D times n minus 1.
What's that?
Would you do D minus n times D minus 1?
Okay, I can barely hear you, but you said something about the n minus 1 times D or something?
Yeah.
What would you want to do with that?
Multiply it out.
Oh, distribute the D in here?
Yeah.
You can do that. Yeah. There's nothing wrong in doing that. You don't have to do that, but you can. Okay. So you're saying maybe the first thing is what you do is go inside the brackets here and maybe distribute the D inside the parentheses. That's perfectly okay to start that way. No harm done. All right. Want to solve for A. Any other advice? How to move from here? Now, what's that?
Let's distribute the n over 2.
Okay, you could distribute the n over 2 inside the parentheses into all these terms here. Or you could forego that. You don't have to do that. Tell you what, I do see a fraction in this equation here. And how could I get rid of this fraction? I could multiply both sides of my equation by what, 2? If I wanted to. So there's different ways of pursuing and solving for A here. All right, that's what we're finding out here very quickly. I'll tell you what, ladies and gentlemen, let me show you a little more efficient way to solve for A here. There's nothing wrong in distributing the D here, although you really do not have to do that here. What we could have done from the get-go is we could have multiplied both sides of our equation by the reciprocal of n over 2, which is to say we multiply both sides by 2 over n. That'll knock this fraction out immediately. So when you multiply the left side by 2 over n, you'll have 2s over n. But you got to multiply the right side by 2 over n also. And whether you distribute this D inside the parentheses or not is entirely up to you. It's not going to make a huge difference. The nice thing now is when you multiply n over 2 by its reciprocal, what do you get for a product? What do you always get for a product when you multiply reciprocals together? This is just going to simplify to 1. So we'll have 2s over n equal, this is just 1. And 1 times this is just this. So you can drop the brackets now. They're no longer serving any purpose. All right, to solve for A, we're going to have to get both these terms over to the left side of our equation. You got to move them both over to the left. So I'm going to have to subtract dn from both sides. And I'm also going to have to add d to both sides. I'm going to kind of take care of both these steps here at once here. So again, what did I do? I'm going to subtract dn from both sides and add d to both sides. When I do that, my left side is going to be 2s divided by n minus dn plus d. On the right side, the dn's drop, the d's drop out. We're left with 2 times a. All right, now we're gonna have to get A by itself, so we'll divide both sides of our formula by 2. And so therefore, I'm gonna have to divide every term on the left side of my equation by 2. So this is gonna have to be divided by 2. This dn is divided by 2, and the d is divided by 2, and the 2a is divided by 2. This is a little bit messy here. I'm going to show you a little shortcut, ladies and gentlemen. When you have a complex fraction where you have a fraction over a fraction, you might want to write this down, or just try to highlight or memorize this in your mind. The quickest way to simplify this complex fraction is to think of it as this way. It always works this way. C comes up and joins A as a factor. B comes down and joins. I said that wrong. Wrong. If you have A over B over C over D, the quickest way to simplify this complex fraction is to bring this D up and join the A as a factor, and the B comes down and joins the C. Hence, this immediately simplifies into AD over BC. Always works that way when you have a complex fraction. You see that little shortcut there? Shortcut. Quickest way to simplify this complex fraction here to here. So in other words, this n comes down and joins the 2 down here. So therefore, we're going to have 2s over 2n minus dn over 2 plus d over 2. And this is equal to a. So technically, we solved for a. We got a all by itself on one side of our equation. This reduces down to 2's drop out, reducing down to 1, leaving you with s over n minus dn over 2 plus d over 2 equals a. And that would be good enough. You could stop right there. We solve for a. All right, that'll work. All right, that's not the only way to solve for a here, but it does work. All right, that's a pretty efficient way to go. Another thing up here is we did not necessarily have to distribute the d into the n minus 1. We could have just, when we got it down to here, we could have just subtracted n minus 1d from both sides of our equation, brought the whole term over to the left side. So you don't have to distribute the d in here, but we chose to do so. And the bottom line is, whatever way you choose to solve for a here, whatever move you make, just make sure it's a valid use of an equality property, and you're going to be okay. And so I have to accept the myriad of potential other equivalent forms for this as solutions for this problem. So this is not the only representation for a like this. There's other equivalent forms for this. Okay. I'm just, throwing that out there, that this is just one rendition for a, but there's other various equivalent forms for this that I would have to also accept as an answer, because some of you may, pursue solving for a slightly differently here. Okay. All right. So don't think that this is the only form I'm going to accept. All right. There's other different equivalent forms of this that I could accept here. For instance, I could accept this form here, which would be just as equivalent. This, ladies and gentlemen, I know it doesn't seem like it, but this is just as equivalent to this up here. Just as equivalent to this up here. They're equal to each other, these expressions. So I would have to accept this also as a possible answer. All right. And you would get this answer had you not distributed the d inside the parentheses up here. So that's entirely up to you. All right, either this or this. I'll accept them both. We're both solved for a correctly. Any other questions about this problem here?
I have a question.
Yep.
When you said that you combined 2 steps after you wrote 2s over n equals 2a plus dn minus d, I'm confused at what you did after that.
It was right here. I wanted to move the dn over the left and the d over the left, so I subtracted dn from both sides of my equation, and I also added d to both sides of my equation. Then after that is then the dn's drop here and the d's drop, correct? And
Okay.
It gets me down immediately down to 2a. I just want to save a little bit of time there because we are starting to fight the clock viciously here. Okay.
Okay. Thank you.
All right. Any other questions about this here? So yeah, keep this in mind about complex fractions, ladies and gentlemen. This is a very quick way to simplify complex fractions. It really saves a lot of time if you're in a crunch, okay? So it always works that way. All right. Here's another formula. Solve for P. This formula here belongs or pertains to the business world. It involves money. The future value in an account is equal to the principal that initially is in the account plus the simple interest that the account earns. Simple interest is principal times rate times time. Principal is an initial amount of money that you sink into an account or that you rack up on a loan or a bill or something. R is the interest rate, percent turned into a decimal, and time is in years. This formula is solved for the future value of an account called the amount. I want to turn the tables on and solve it for the principal. Anybody know how I can solve for P here? Anybody got any advice how I want to solve for P? How I can solve for P there?
Divide by RT.
All right, we could divide both sides by RT. Nothing says we can't do that, but you got to divide each term on both sides by RT. And when you do that, you'll have this. Now, the nice thing here is the RTs drop out, leaving you with P. All right, you want to solve for P. That's perfectly legal to do. Does that make our situation look less complicated or more complicated? What do you think, ladies and gentlemen? Less or more complicated? Well,
Complicated.
it does in a way a little more complicated. I mean, look, we still got, see, initially we have P divided up into two different terms here. We still got P separated in two different terms on the right, but we have an added complication where we have fractions that have seeped into the picture. I mean, you can do this. There's nothing wrong in dividing both sides by RT. And if you know where to go from here, you can still solve for P. But, I don't know. Looks kind of messy, doesn't it? Well, any other advice? What we could have done up here from here? It's not obvious, but anybody have an idea?
Couldn't you just add the P's together?
Okay, you know, somebody said that in my section earlier this morning. That's awesome. Yeah, I mean, you know, why can't we just add these terms together? They both have a P in them. Well, why is this not a like term with this term here? Why not?
It doesn't have the RT.
It doesn't have the R and the T also. These are not like terms. Yep, can't add them together. Nice try, though. Hey, I'll give you that. Well, ladies and gentlemen, I'll give you a hint. Let's concentrate on the right side. What can I do that at right side there? No, we can't add those terms together. They're not like terms. Last week, I think I ran you through how to blank a bunch of polynomials. And what goes in the blank is a word that starts with the letter F. I showed you how to factor. There's your key hint, ladies and gentlemen. What can I factor out of both these terms on the right side of my equation? What can I factor out? They both share what factor in common?
P.
P. Let's factor P out. When I factor P out, I leave behind 1 plus RT. True? Now to get P by itself, we divide both sides of our equation by this whole binomial, 1 plus RT. And there you go. We have solved for P. Because the 1 plus RT, the whole factor reduces out here to 1. And we're left with P equal to A over 1 plus RT. That is the most efficient way to solve for P in that formula there. Everybody see that there? That's not to say it's the only way, but it's probably the most efficient way. Definitely. Everybody see that, how we did that there? So the trick here was factor P out of both these terms to consolidate it to showing only once on the right side. But that was not obvious though. That's why it was kind of difficult. It wasn't obvious. All right, classwork number 1. I want to have you maybe try a problem or two, maybe solving an equation or so. So we'll call this classwork 1. Today is the 24th day of January. All right, just make sure you email this to me by midnight tonight. What are you going to put in the subject line of your email? What do we put in our subject line? We say math 130 dash what? Hybrid 01. Do you agree? Please put that in the subject line of your email so that I know from whence it's coming. All right, ladies and gentlemen, here's what I want you to do. Problem number 1. I want you to solve. I want you to solve this equation here. 2 over x minus 5 minus 1 over x plus 5 equals 11 over x squared minus 25. I want you to solve this equation for the variable x. Question number 2. I want you to solve C equal to 5/9 times F minus 32. I want you to take this formula and I want you to solve for the variable F. This formula pertains to temperature, Celsius versus Fahrenheit. This is a conversion formula that enables us to convert from Fahrenheit to Celsius. I want you to turn the tables and solve for F so that we can convert from Celsius back to Fahrenheit. Solve for F. All right, I'll give you some time to work on those. We'll call that classwork number 1. Okay. So that would be the solution to the first question on classwork number 1. X equals -4 there. All right, now solving this formula for the variable F, probably the most efficient way to go about this, although you could distribute the 5/9 inside the parentheses. That's just going to lead to more fractions appearing everywhere. I decided to get rid of this fraction by multiplying both sides by the reciprocal of 5/9 by multiplying both sides by 9/5. And by multiplying both sides by 9/5, I immediately knock out this fraction of 5/9. And then I just add 32 to both sides of my equation. And I have solved for F in terms of C. Did anybody pursue the problem that way? Just curious.
I did.
Okay. Now, don't feel bad if you didn't do it this way. There are, equivalent versions for this. Some of you may have chose to distribute the 5/9, inside the parentheses first. In which case you would have minus 160 over 9. And you would add 160 over 9 to both sides in the end. So there are equivalent versions for this. In other words, if you decided to distribute the 5/9 inside the parentheses, you would have this. And you could add 1/69 to both sides. But then you're still going to have to get F by itself, so you're going to have to divide both sides by 5/9, which is equivalent to really multiplying both sides by 9/5. So you're really going to have to multiply both sides by 9/5. Then you could distribute the 9/5 inside here and have 9/5 C plus 9/5 times 160 over 9. The 9's cross cancel out, and you're left with 160 divided by 5. 160 divided by 5 reduces down to guess what? 32. Same answer. You agree? All right. Same answer. All right. So that section is in our rear view mirror. Okay, ladies and gentlemen, now we're going to wrap up today's session by looking at some word problems in section 1.2. And getting good with word problems takes time. It took me years to perfect these things. But if you never start somewhere with word problems, you never will get better with them, ever. It'll never happen. And so the way to learn word problems is to see a lot of them done and then try to emulate the procedure by doing similar problems. That's the part of the learning process. Okay. So I'm going to go to section 1.2, and it's entitled Applications with Linear and Rational Equations. In other words, when you see the word applications, that means word problems, right? In this purple shaded box here, or outline box, they give us some things to keep in mind as we try to negotiate word problems. First, you want to read the problem carefully, and you may have to reread it several times. Don't feel bad about that. Very important part of any word problem is properly assigning your unknowns with variable or variable expressions. Your accuracy in doing so or lack thereof could make or break your word problem a success. If you can draw a picture or use a table, by all means, do that. That better helps you to zone in on the situation. Ultimately, steps 1 and 2 are designed to help us lead to an equation that we're trying to set up. And once we set up the equation, then it's usually pretty easy just to solve the equation. And last but not least, you want to make sure your answer checks out as far as reasonableness is concerned. In other words, if you're doing a problem involving the speed of a car and you end up with a solution where the speed of the car is like 60,000 miles per hour, then you probably made a mistake somewhere, correct? So you always want to check your answer for reasonableness. Does it seem reasonable? If it does, chances are you probably did things right. If it's not reasonable or don't seem reasonable, chances are a mishap occurred somewhere. I'm going to try to do several of these problems. And again, outside of class, I strongly recommend that you look over these examples in this section because your author gives you different looks that you may not see when on the problems that I demonstrate in class. This is only going to make you more experienced and make you more robust in attacking all word problems is by spending a little time and going through these examples that your author lays out nicely, even in color here too. So please take the time to look at some of these examples in all the sections that are covered. It's only going to enhance your understanding of college algebra. And it's going to lead to good things as far as grades are concerned. Okay. All right, the first one I'm going to attempt here is problem number 8. It says Laura borrowed a total of $22,000 from 2 different banks to start a business. One bank charged equivalent of 4% simple interest, and the other charged 5.5% interest. Now, so there's 2 different accounts, 4% and 5.5% simple interest. If the total interest after 1 year amounted to $910, they want you to determine the amount of money that was borrowed from each bank account. Okay. First of all, you have to clearly understand what it is you're being asked to find. If you don't understand that, then there's usually no hope. They want us to find the amount borrowed from these 2 accounts. When I get done, how many answers am I going to have to this problem when I'm done? Anybody?
2.
2. One, the amount of money borrowed from the 4% account and the amount of money borrowed from the 5.5% account. All right. What makes word problems challenging is that everyone's different. Some pertain to money, some pertain to solution mixture problems, some pertain to distance, speed, and time. All right. And that's what makes them challenging. The only way you're going to get good at these is by seeing a whole bunch of them done and then trying to, duplicate the effort on similar problems. So to help us out here, ladies and gentlemen, what I'm going to do is I'm going to make a table. And for problem number 8, my 2 row headings are going to be my different accounts. I have a 4% account versus a 5.5% account. My column headings are going to be the variables that come in a formula called a simple interest formula that we need to bring into the picture since we're talking about interest. Simple interest is principal times rate times time, and that gives you the amount of simple interest. This is called a simple interest formula. We need to bring that into our problem. So I have a principal column, a rate column, a time column, and an interest column. Now we're going to try to populate this table by reading our problem again. It says we have $22,000. We borrowed a total of $22,000. We don't know how much we borrowed from the 4% account, and we don't know how much we borrowed from the 5.5% account. Because of that, I'm going to declare my variable X to be equal to the amount of money borrowed from the 4% account. So I borrowed X dollars from the 4% account. X is my principal. That's the amount of money we borrowed. But I borrowed a total of $22,000. So X of that $22,000 went into this account. So what would be a variable expression that represents the remaining amount that went into the other account? Anybody? What would be a variable expression that represents the remaining amount that went into the other account? I borrowed a total of $22,000. Well, you could use a different variable Y, but then we're going to involve ourselves in a system of two equations and two unknowns, and we're not into that yet. Okay. We want to try to keep it down to one variable. So I borrowed a total of $22,000. X of it went into this account. What would be a variable expression that represents the remaining amount? That goes,
22,000 minus X.
there you go. $22,000 minus X dollars would be a variable expression that represents the amount of money borrowed from the other account. So this is the amount borrowed from the 5.5% account. And again, you could use a different variable Y, but again, we'd be solving a system of two linear equations and two unknowns, and that's not really the focal point for this section here for these word problems. All right, so I'm going to put 22,000 in here minus X. Now, 4% as a rate, as a decimal, is 0.04. 5.5% as a decimal is 0.055. Percents are turned into decimals by shifting decimal point 2 places left, dropping percent symbol. We borrow this money from both accounts for 1 year. How much interest is accrued from the 4% account? Where interest is principal times rate times time. So the amount of interest that we rack up from the first account, having borrowed X dollars, is going to be 0.04 times X times $1. The amount of interest that we rack up from the 5.5% account, having borrowed 22,000 minus X dollars, is principal times rate times time, which is going to be 0.055 times 22,000 minus X dollars. Okay. But they said that we racked up a total of how much interest? At the end of 1 year, we racked up a total of $910 of interest. I'll put a total column down here, a total row rather. And so, ladies and gentlemen, I can now set up my equation. I claim that my last column enables me to set up an equation. What would that equation be? What am I going to do with these interests here? What am I going to do with them? These interests. Well, since my total interest is $910, the total.
Are you going to add them?
That's right. We add up the interest accrued from each account. So this is the amount of interest that the 4% account racks up, added to the amount of interest that I rack up from the 5.5% account. And totally, that better amount to $910 of total interest over 1 year. We now have our equation, and now hopefully we can solve this equation for the variable X. Now, in order to solve this equation, what would I have to multiply both sides of my equation by if I wanted to get rid of my decimals? Would 10 be good enough? Or would I have to multiply both sides by 100, or maybe 1,000, or 10,000, or 1,000,000? What would I have to multiply both sides by to make all my decimals become whole numbers?
1,000.
Yeah, 10's not good enough because we'll still have 0.4 here. 100's not even good enough because I'll still have 5.5 here. I would have to multiply both sides by 1,000. All right. And so I would multiply both sides of my equation by 1,000. And when I do that, this would be the solution. So here we go, ladies and gentlemen. I multiply both sides of my equation by 1,000. 1,000 times 0.04x gives us 40x. 1,000 times 55 thousandths gives us a nice whole number of 55. 1,000 times 910 gives me what over here? 910 what thousand? Now solving for x, I distribute the 55 inside the parentheses here. This 55 gets distributed in here, in which case I will have the left side looking like this. I combine my like terms. 40x minus 55x is minus 15x. Continuing to separate now. I got my variable on the left. I want to take this constant 1,210,000. I want to take this over to the right. So I subtract 1,210,000 from both sides of my equation. 1,210,000 drops out on the left, leaving me with negative 15x. 910,000 minus 1.21 million gives me what, 300,000? Then I divide both sides of my equation by negative 15, and I discover that I borrowed $20,000 from what account? What was X declared to be? X was declared to be the amount that was borrowed from the what account? The 4% account, correct? So I borrowed $20,000 from the 4% account, which means I borrowed 22,000 minus 20,000 or $2,000 from the 5.5% account. Isn't that true? And we're done with that problem. We now know how much we borrowed from each account. That's a classic or typical simple interest problem. All right. Questions how I got that?
Can you go back to the bottom real quick? Okay.
Right there. So I will be assigning you similar problems like this. And the way these problems have been demonstrated is exactly the way you're going to demonstrate your problems. Same path. You walk down the same path. And again, please do look at some of the examples in this section. That's going to only enhance your understanding of how to solve other types of word problems, problems that maybe I don't have time to get to in this session here. Please do look at those examples. You know, when you do your Alex homework, off to the right side, you have a button you can click on that says, show me an example, and it'll walk you through a similar example that you're being asked to do step by step by step. That's an invaluable button for learning how to do your homework if you're still stumped. Now, unfortunately, that button does not exist on quizzes or exams. That button is removed, but it is available on homework though. All right. And you have an unlimited number of attempts on your homework to maximize your grade. All right. Any other questions about this problem here? All right. Now, another problem that I would like to look at is, what is it here? Number 12. See all these practice problems here, ladies and gentlemen? And I'm going to give you the solutions to every one of these, odds and evens. Loads of extra practice to hone your skills on word problems. I'm going to try number 12 here. A nurse mixes 60 cc's, that's 60 cubic centimeters of a 50% saline solution with a 10% saline solution to produce a 25% saline solution. How much of the 10% solution should he use? This is a classic mixture problem, solution mixture problem. Saline solution is a liquid solution that consists of so much pure salt dissolved in so much pure water. Okay. And when I do a mixture problem, I tend to kind of like use a diagram like this. And I'm going to go to my dot cam in a second. Just hold on. Okay. So let's go back to my my dot cam here. All right, I'm going to add so much of a solution to so much of a pre-existing solution to give me some sort of a total solution or final solution. All right. Now, in this word problem, I'm going to go back and read it again. We're going to take 60 cc's of a 50% saline solution. Now, when you do these solution mixture problems, you need to be consistent with what it is you're talking about all the way across your equation. In other words, you need to talk about so much pure water being added to so much pure water to give you so much pure water. Or you need to be talking about so much pure salt added to so much pure salt to give you so much pure salt. You cannot mix this up. It won't work. You can't say so much pure water added to so much pure salt to give you so much pure salt. No good. So you got to be consistent in what you talk about all the way across. I'm going to talk about pure salt all the way across. Pure salt. So if I have a 50% salt solution, how much of it is pure salt? Well, 50% of my volume. All right, so the amount of pure salt in my first solution is going to be 50% of 60 cubic centimeters. That's the amount of pure salt that I have in my first solution here. Now I'm going to add that to an unknown volume of my 10% saline solution. And since we're being asked to find out what that volume of the 10% saline solution is, and we don't know what it is, you might want to declare it as a variable x. I'm going to call it x. So I'm going to let x be equal to the amount of 10% saline solution added. I want to get a final solution, and my final solution has to be a 25% saline solution. So, ladies and gentlemen, what would be the final volume in my final mixture here? What would be a variable expression that represents my final volume? Anybody?
60 plus x.
Yeah, 60 cubic centimeters added to x cubic centimeters. Instead of saying 60 plus x, I'm going to spin it around and say x plus 60. Same thing. And there we go. We really have a crude equation here staring at us in our diagram or our picture here. And to refine it into an equation, we ask ourselves, how do we take the percent of a number? Change the percent to a decimal, and of means multiply in word problems. So 50% of 60 cubic centimeters is going to be 0.50 multiplied by 60. This is the amount of pure salt in cubic centimeters for the first solution. Added to how much pure salt in the second solution? Well, it's going to be 10% of x cubic centimeters. How do you write that? How do you write 10% of x? It's going to be 0.10 times x. That's the amount of pure salt in cubic centimeters from the second solution. Together, when you add so much pure salt from the first to so much pure salt of the second solution, it better give you so much pure salt in the final solution. How much? Oh, that'll be 25% of x plus 60 cubic centimeters, which is written as 0.25 times x plus 60. And there you go. We now have our equation set up for x. All we have to do is solve the equation for x. And that will indicate how much of the 10% saline solution must be added in to have us realize the final solution. What would I have to multiply both sides by? What power of 10 to eradicate all the decimals? All the decimals. Want to get rid of all of them. What do you think?
100.
100. Yeah, 10's not good enough because this will still be 2.5. I'm going to multiply both sides of my equation by 100. That way, I will knock out every one of these decimals. So let's do that. Multiply both sides by 100. That means 100 gets distributed in to all these terms on both sides. And when I do that, ladies and gentlemen, this is what we're going to be looking at for a solution here. So I multiply the left side of my equation by 100 and the right side by 100. 100 times 0.50 or 50 hundredths is a nice 50. 100 times 10 hundredths x is now nice 10x. 100 times 25 hundredths is a nice 25 now. The decimals are gone. Continuing onwards, distributing the 25 in the parentheses on the right. Separation time, bring the 25x over to the left by subtracting it from both sides, and bringing the 3,000 over to the right by subtracting 3,000 from both sides. Now, I did leave off a subtle step in here that's showing that I subtracted 3,000 from both sides and subtracted 25x from both sides. I just went from here to represent that. Everybody understand what just happened? From here to here. I subtracted 25x from both sides, and I subtracted 3,000 from both sides. Combining like terms on both sides to further simplify both sides, we get it down to this. Dividing both sides by negative 15, we discover that we have to add in 100 cubic centimeters of the 10% saline solution to achieve our final saline solution. That must be 25% in concentration as far as salt is concerned. Everybody understand how we got that there? That's your answer. 100 cc's of the 10% solution must be added in. That's a typical solution mixture problem. Anybody see that there? That's a very typical solution mixture problem there. Doesn't really get any easier than that for a mixture problem. All right. Any other questions on that one there? Okay. Let's go back to our textbook. Another one I want to do is one like number 18 here. This is a rate problem, distance, time, rate. Peggy competes in a biathlon by running and bicycling around a large loop through a city. She runs the loop 1 time and cycles through the loop 5 times. She can run 8 miles per hour and she can ride her bike at a speed of 16 miles per hour. If the total time it takes her to complete the race is 1 hour and 45 minutes, determine the distance of the loop. They want us to find how long this loop is in the city. How many miles long is this loop? That's what they're asking us. This is a classic distance, rate, time problem, ladies and gentlemen. And so we're going to look at this one here. Problem number 18. Now, my rows of my table are going to be the 2 different situations that Peggy is finding herself in. She's finding herself in what? What was the first one? Running. So I'm going to have a running row in my rate table, and then I'm going to have a cycling row in my rate table. Let's go to my doc cam here. All right, running versus cycling. And the column headings are going to be the variables that are going to be in the formula that relates distance, rate, and time. The distance an object travels is equal to the rate or the speed with which it travels times the time that it travels at that speed. So I have a distance column, a rate column, and a time column. That's my rate table. And now I'm going to try to populate this rate table based on the given information in the word problem. Now, the presupposition in this problem is that the speed with which Peggy runs and she cycles is constant throughout the problem. If Peggy's speed, ladies and gentlemen, is speeding up or slowing down constantly through time, then algebra cannot address that situation. To address that, you would have to use a more sophisticated branch of mathematics, which is called integral calculus. Integral calculus was designed to address questions that algebra simply cannot answer. What happens if your speed is constantly changing through time? Calculus was designed to deal with variables very efficiently with variables that constantly change through time. Algebra cannot deal with that. Algebra only presupposes that our speed remains constant. We get in the car, we drive 50 miles per hour for 2 hours. We've gone 50 times 2 or 100 miles. That's algebra. But if we're constantly speeding up or slowing down on the road, then algebra falls flat on its face in answering how far we will have traveled in 2 hours. You would have to use calculus to answer that question. Okay. But, ladies and gentlemen, trust you me when I say this, the most difficult part of calculus, you ready for this, is not really the calculus. It's the algebra. Any student will tell you that. So therefore, ladies and gentlemen, if you are going to go into calculus someday, you might want to strengthen your algebraic skills. You're going to need a strong algebraic base to succeed in calculus. Okay? I'm not trying to scare you. I'm only being realistic and honest. The toughest part of calculus is the algebra. The algebra becomes quite intense at times in calculus. So you want to have a strong algebraic base if you're going to go into calculus. All right. All right. In other words, if you failed algebra, if you fail algebra miserably, yeah, you're going to struggle in calculus big time. That's the way it is, unfortunately. All right, so let's try to populate this table here. What do we know? We know that Peggy can run around this loop at what speed? She runs at a speed of 8 miles per hour. That will go in for the rate at which she runs, 8 miles per hour. She can cycle around this loop at a speed of 16 miles per hour. That goes in for the rate for cycling. Now, it says she completes this biathlon in 1 hour and 45 minutes. So I have a question for you. Does that mean that she spent 1 hour and 45 minutes running and also 1 hour and 45 minutes cycling? Yes or no? Do I put 1 hour and 45 minutes in for both these times?
No.
No, that's not what it's saying. It's saying the total time to complete this biathlon, which involved some running and cycling, was 1 hour and 45 minutes. All right. And furthermore, ladies and gentlemen, we don't know the distance of this loop. We don't know. In fact, why don't we declare that as a variable? Let's say let x be equal to the length of the loop in miles. They're asking us to find this. Well, how many times did she run around this loop? Well, it says that she ran around this loop one time. So if she ran around this loop one complete time, what distance did she cover? She covered 1 times x what? Miles. This is the distance that she ran around the loop because she ran around it only one time. And this is the length of the loop. But she cycled around the loop 5 times, each time covering x miles. So what would be in a variable expression? It represents the total distance covered by cycling. 5x miles is the total distance that she bicycled around the loop because she went around 5 times. What do we put in for time, though? This is one of the most difficult aspects of this problem. What do we put in for time into this table, though? That's a big mystery. Well, here's what we're going to have to do. We know that distance is equal to rate times time. Let's solve this formula for the variable time, t. How would I solve for t? Divide both sides by r. So therefore, time is equal to distance divided by speed. Time is equal to distance divided by the speed or the rate. So how much time did she spend running around this loop? That would be her distance running around the loop divided by the speed with which she ran around the loop. So the time she spent running around the loop would be x miles divided by 8 miles per hour. This is time. Distance divided by rate is time. How much time did she spend cycling around the loop? If she covered a distance of 5x miles, traveling at a rate of 16 miles per hour. Well, the number of hours she tied up in cycling around the loop would be distance divided by speed. 5x miles divided by 16 miles per hour. These represent times. What am I going to do with these times if we know that the total time that it took her to do this biathlon is 1 hour and 45 minutes? What fraction of an hour is 45 minutes? How many minutes in an hour? There's 60 minutes.
3/4.
Yeah, so this would be 3/4. It would be 45/60ths of a what? Hour, correct? 45/60ths is a decimal is 0.75. So this is going to be 1.75 hours. That's how much time it took her totally to complete this biathlon. 1.75 hours. From the last column of this rate table, we can set up our equation. If we take the time that she spent running and add it to the time she spent cycling, that better be equal to the total time to complete the biathlon. Here's your equation. X over 8 hours plus 5x over 16 hours better be equal to 1.75 hours totally. And now we just solve for x. So how would we solve this equation for x? Well, we could get rid of the fractions. I know we got a decimal there, but we could get rid of these fractions here by multiplying both sides by the least common denominator, which would be 16. I believe that's what I did then, is I did multiply both sides of the equation by 16. Okay. And later on, when I did that, I got this here. So I multiplied both sides of my equation by 16. My equation then collapsed down to this. All the fractions are gone, and the decimal disappears too. How nice is that? And then I just, combine like terms to the left, divide both sides by 7, and I get x equals 4. So that would be the length of the loop. The loop is 4 miles long. Does that make sense how we got that length of that loop? It's a 4-mile long loop.
Could you go back like underneath the paper again?
Okay, that was over here. Notice I declared my variable x as the length of the loop. Your declaration part of your word problem is a critical part of any word problem. You got to properly declare your unknowns, because if you don't, you got nothing to work with then. And it's going to be extremely difficult, if not impossible, to set up an equation. Okay. All right. So any other questions about this basic rate problem here? Your standard run-of-the-mill rate problem. In this case, running versus cycling. Sometimes you have other cases where you have airplane B versus airplane A. Or maybe boat A going upstream versus boat A going downstream. Distance, rate, time problems. Okay. The only way you're going to get better at these is by seeing a whole bunch of them done. That's why I strongly recommend you try to do extra practice in your textbook and then look at the solutions if you get stumped and study the solutions so you can understand how the problem was done. All this is going to enhance your understanding as to how to attack word problems in general. And you're going to become more experienced and more mature. And one day you'll look back and laugh at these word problems, thinking at one time in your life you were totally stumped and unable to do them. Okay. It takes time though, but that time involves work, investigating how to do these things. All right. And being shown how to do some of these problems. That's why I'm trying to do my part, at least point right now. But you also have to go above and beyond that and start to entertain some of the problems on your own and look at their solutions and study them. All right. Rate problem, ladies and gentlemen. All right. I also want to do, and I'm running out of time. I'm down to almost 10 minutes left. Number 22. Brad and Angelina. Not sure if these are the actors, but whatever. Brad and Angelina can mow their yard together with 2 lawnmowers in 30 minutes. When Brad works alone, it takes him 50 minutes to do the job. Question is, how long would it take Angelina to mow the yard or the lawn working all by herself? This is a classic division of labor problem. All right. And so we're going to wade into this problem here. All right. Now, when these two people work together, ladies and gentlemen, we are presupposing that they work together well. In other words, they don't get in each other's way and slow each other down, because if that was the case, this problem is not valid. All right. But in general, normally when we pool our labor and we have more people helping out on a job, we can finish the job quicker. In general, that's the way it works, or is supposed to work. All right. Notice Brad requires 50 minutes to do the job all by himself. Angelina, we don't know how many minutes, and it takes 30 minutes for both of them working together to complete the job. So here's what we're going to do. We're going to get into this problem now. Ladies and gentlemen, we know that Brad can mow the yard in 50 minutes. They told us that. Therefore, at what rate does Brad mow the yard? Well, the rate with which Brad mows the yard is going to be the reciprocal of 50, which is to say that Brad can mow 1/50th of the complete yard per every 1 minute. Why is that? Why is it 1/50th of the yard per minute? Why is that the rate with which Brad can mow the yard? Think about it. Because it's not too difficult to see that after 1 minute, Brad will have what? Completed 1/50th of the yard. This is after 1 minute, correct? But after another minute, he will mow another 1/50th of the yard. This is 2 minutes later. Plus, after 3 minutes, he will mow another 1/50th of the yard. That's 3 minutes later. Plus, but how many minutes does Brad got to work to finish the yard? $50 minutes. So when you add 1/50th to itself 50 times, that's equivalent to like taking 50 times 1/50th, which is really saying that Brad will have completed 50/50ths of the yard, which is to say that Brad will have completed 1 whole yard. Does that make sense? So if Brad can mow the yard in 50 minutes, that means Brad works at a speed of 1/50th of the yard being mowed per every 1 minute that goes by. Now, we don't know how long it takes Angelina to mow the yard, therefore we'll call it X. We'll say Angelina requires X minutes to mow 1 whole yard. Therefore, the rate with which she mows the yard will be 1/X of the yard per minute. But they're both going to work together for 30 minutes to complete 1 whole yard. And so, ladies and gentlemen, the fraction of the yard that Brad will complete in 30 minutes, working at a rate of 1/50th of the yard per minute, is going to be 30 times 1/50. This will be the fraction of the yard completed by Brad, plus the fraction of the yard that Angelina completes, also working for 30 minutes, would be 30 times 1/X of the yard per minute. 30 minutes times 1/X yard per minute would give you the fraction of the yard completed by Angelina. Together, these fractions of the job completed better add up to equal 1 whole yard having been completed. That's why these fractions must add up to 1. We have an equation now, and now we can solve for X. And to solve for x, I would multiply 1 over 50 by 30 and 1 over x by 30. And when I do that, ladies and gentlemen, I would have this equation here that I have to solve for x. Common denominator would be 50x. So I multiply both sides of my equation by 50x. When I do that, the fractions disappear through reducing or cross canceling. Fractions drop out everywhere. And this is the equation I have to solve for x now. To do so, what did I do? I subtracted 30x. I actually brought 30x over to the right side of my equation this time. I just chose to do it that way. By subtracting 30x from both sides, the 30x came over to the right to join the 50x. Equation collapsed down to this then. 50x minus 30x is 20x. Divide both sides by 20, and I get x is equal to 75. So therefore, Angelina requires 75 minutes or 1 hour and 15 minutes to mow the whole yard working alone. That's the time required by Angelina, 75 minutes or 1 hour and 15 minutes. And we're done with this problem. Okay.
Could you go back to the part that was like above the Brad can mow, like all the information you put?
Yeah, it was right here. This is the original problem here. Before
That
I
was it. Okay, then I got it.
this was the initial part of the word problem before I started solving this equation, and I showed you how to solve the equation. Okay. All right, that's that. And remember, this is recorded, so you can always go back over the recording at your leisure and pause me and do anything you want. Okay. All right, so yeah, Angelina requires 75 minutes to do the job. Ladies and gentlemen, there's just one more problem that I want to show you in our textbook. One more, and then we're done. All right, this last problem is number 28, one like 28. This is interesting. To estimate the number of bass in a lake, a biologist catches and tags 24 bass. Several weeks later, the biologist catches a new sample of 40 bass and finds that 4 of the 40 are tagged. So 36 of the 40 caught bass are not tagged, 4 are. How many bass are in this lake? I claim, assuming that none of these bass are able to leave or enter into this lake from some other water source, ladies and gentlemen, that if it's like a self-contained lake, this is a pretty good example of how to estimate the total population of bass in the entire lake without actually having to go out there and take a census. All right. And you know how we can do that? We can set up a proportion. All right. So here we go. I'm going to show you the proportion we'll set up to answer this word problem here. And here it is. Now, when the biologist went out and caught some bass, initially 24 bass were tagged. They came out a couple weeks later and caught 40 bass and discovered that of the 40, 4 were tagged. We're going to let X be equal to the total bass population in this body of water. So we can set up a proportion. We can say 24 tagged bass is to X total bass in the lake as 4 tagged bass out of 40 that were caught weeks later. Now, when you set up a proportion, you got to make sure your units are the same across. Tagged in the numerator, tagged in the numerator. Total in the denominator, total in the denominator. That is important to be consistent with your units across when you set up a proportion. Okay. All proportions enjoy this property. That is to say that the cross products are always equivalent to each other. So I would take 24 times 40 and set that equal to 4 times X. Ladies and gentlemen, dividing both sides by 4, I discover that a good estimate as to the bass population in that entire lake would be to say that there's 240 bass in an entire lake. And again, the accuracy of this estimation depends upon the requirement that this is kind of like a self-contained lake where bass are not able to leave or come from some other water source. If they were, it would become a much more difficult problem to deal with. Okay, so this is a rather simplistic situation, but nonetheless, hey, you got to admit this is pretty cool. So, you know, keep that in mind. If you ever have like a large pond and you want to estimate the total number of, like, let's say sunfish in the pond, maybe you could catch like 10 sunfish, tag 5 of them, release them, come back, catch some sunfish, and out of the ones you catch, how many are tagged, and then you can set up a proportion estimate. Pretty neat, huh? It's a lot better than going down and with scuba gear and trying to count all the bass and tell the bass to stay still. Don't move. I need to count all of you. Okay. All right, ladies and gentlemen, that's it. I've worn out my welcome. I will update the homework for these sections on Alex. I will open up 1112. I will also post the solutions to 1112 homework in your text, the solutions to the textbook homework problems. Should you want to do extra practice, please do. And I think that's it. So I'll stay on the line if there's any other questions or concerns. If not, have a great day, and hopefully I'll see you in a couple of days.
Hello.
Okay, you got a question?
Yeah.
Alrighty.
If we like needed to meet with you one-on-one or
Uh,
anything, could we come in and see you like in class? Because I know I had your in-person class last semester. So, or would you?
well, you could do that. Probably the more efficient way is, you could maybe arrange like a little Zoom session with myself. I can set up a little Zoom session and we can meet that way if that would be more convenient.
Yeah. Do you know when that's possible for you?
Okay, let's see here. Let me look at my schedule, okay, and I'll get back with you. This is Julie, correct? No, this is Olivia.
Yeah.
Olivia. Okay. All right. So Olivia, I will look at my schedule and I'll see if I can arrange maybe a brief time to get back with you. Would that be this week then, or what?
Yeah, just as soon as possible. I just have like a few questions with like the homework and everything and like stuff like that.
Okay, well, I'll tell you what, I got a little time now. If you have the homework problems, I'll be more than happy to hash them out with you. I got a little bit of time right now, a couple minutes.
Okay, I mean, for me, it's just mainly about like the credit and stuff that like we're gonna be getting for it. So, let me see if I can turn this on.
Okay.
So, so when you do the problems, you only get a certain amount of tries, and so like marks it as incorrect. But then you get to like see how it's worked out. Well, you would have to retake the whole entire thing to like get 100%, and even then the questions aren't the same. But I've been doing it like I've just been fixing it and doing the example problems that come with it. So
Now, are you referring to the homework problems on Alex?
yeah.
Okay. Now I'm going to go back and make sure that I have it geared so you can do a quick retake, which means you only have to retake the ones that you got wrong.
Okay.
Instead of having to redo the whole thing. All right.
All right. And then
I could have swore I arranged it that way, but I'm gonna have to double check that. Okay.
Okay. And then during the quick retake, is it going to be the same question or is it going to be different? Because
well, I mean, it's not going to be exactly the same numbers. Probably the numbers will be different, but it should be a similar type of question. Okay.
Okay.
Should be very similar. Yeah.
Yeah, I was just wondering because in your in-person class, you had us just turn in the assignments
Yeah.
Yeah.
Yeah, I know, on exam day. Yeah.
Yeah, I was just wondering if we redid it and like did an example problems as well, if you would take that for credit, or do you want us to just redo it, retake the whole thing?
Well, it will probably be a quick retake again, where you only have to do, redo the ones that you got wrong, and you can keep doing that till you maximize your grade, and ultimately the highest grade will be taken for your homework assignment. Okay. So, I mean, conceivably, you got to what is it, like for chapter R, it's like February 7th. I mean, you could redo that thing many times, correct, between now and February 7th, right, to try to maximize your grade on the homework.
Yeah, and then also with the exams, and like in your in-person class last semester, you would give